Now, I mentioned the muscle. Of course, muscle have a lot of mitochondria, and they use it. Muscle uses mitochondria, including a lot of oxidative glycolysis, a lot of beta oxidation of fats, so lots of fat burning, lots of glucose burning happening in the mitochondria. But there is a cell that flows through the blood which does not have mitochondria, and that is the red blood cell. Because the red blood cell does not have any mitochondria within it, its only method of obtaining energy is through the only nutrient that can be metabolized or catabolized outside of the mitochondria. So glucose is the only fuel that can be burned or used without reliance on the mitochondria, or the only one that has a non-oxidative potential to it. And thus the red blood cell, which lacks mitochondria, must rely on non-oxidative glycolysis 100%. It is completely reliant. Thus, the red blood cell produces a lot of lactate because every time it's using glucose for energy, which is the only source it can use, it's producing lactate. And again, at the end of it, all lactate is coming from pyruvate, and all pyruvate is a consequence of glycolysis. One of the things that I'm most grateful for through the course of my PhD in bioenergetics was a history of bioenergetics. Ever since that class, I'd never had a class that touched on the history of science, who were the people who made the seminal discoveries in whatever topic we were discussing. But ever since then, I can't help but also want to do the same. So let's just go through a brief history lesson of lactate and the science surrounding it, because there are some really neat people who ought to be acknowledged because of their contributions to what we know now. I think it's really a shame if we don't recognize the efforts of those who've gone before us. Now, the first individual I would mention, and there are others beyond the few that I will bring up here. The first is Otto Meyerhof. Otto Meyerhof was a German biochemist who really led our understanding of muscle metabolism in particular. Now, in the early 20th century, Meyerhof discovered that if you could take a limb of an animal and force it to continue to contract, so force it to undergo extreme exercise, it would start releasing a lot of lactate. So he was the first one to see that if he put the working leg in a little chamber that was depriving it of oxygen, then even lactate would even be produced more readily and in much higher amounts. So he was the first one to start really teasing out lactate not only being a sign of intense exercise, but also more heavily produced based on the oxidative availability and potential of tissue. So connecting glycolysis to lactate, that was really his main finding, which was called the Meyerhof cycle. This idea of lactate turning of glucose turning into lactate through its metabolism. In fact, this discovery was so relevant and considered novel and important that he won the Nobel Prize in 1922 for this work. So Nobel Prize winning work. And it's to him we owe our gratitude, appreciating the origins of lactate in the first place, namely connecting it back to glycolysis. Now, that's not it. We're not done yet. So he found that glycolysis would produce lactate if it's non-oxidative in its origins. But then it was another group who I really appreciate because they found one of the fates of lactate. Up until that time, including Meyerhoff's work, lactate was absolutely considered a waste product. It was just metabolic garbage. And even worse than just benign trash, it was considered harmful, as you heard, as you've heard before. So again, at best, lactate was considered just benign waste product that would somehow need to be eliminated. At worst, it was also considered a contributor to muscle fatigue and muscle soreness. Why are you feeling the burn? It's because of lactate. That's just not true. That's not why you feel the burn. Lactate has nothing to do with that. So that is where it sort of ended. Meyerhoff's work identified lactate as a product of non-oxidative glycolysis. And then what the lactate did after that, well, who knows? Well, then we come to the CORIs. This is, I say plural, this is CORI, Carl and Gertie Cori. This is a husband and wife team of biochemists who made really groundbreaking contributions to understand carbohydrate metabolism, including the role of lactate. So we have Gertie Cori, who I will skip to the end of their story, was the first woman to win the Nobel Prize in Physiology or Medicine in the mid 1940s, and then her husband Carl, who shared the Nobel Prize. Let's just pause and appreciate how cool that is. That the CORI cycle, which is what I'm talking about now. We mentioned the Meyerhof cycle, the creation of lactate from glucose. The CORI cycle is mind-blowingly cool because it represents some incredible recycling of molecules within the body in a way that would seem impossible. That it's like this idea of like a continual motion machine, you know what I'm talking about? This idea that you have something that can continually replenish itself. That's sort of what the CORI cycle identifies here, as I'll get into. But again, this is a Hungarian couple. Carl and Gertie. This was a couple of biochemists, married couple working together on this who identified it. It's really, really neat. Now, what is so neat about it? They identified this cycle of lactate production from the working muscle, and then the lactate would be exported. There are transporters that fit lactate, that enable lactate to move in and out of a cell. That's a very important point that we'll come back to. Now, it's not a surprise that lactate can move out of a cell. Meyerhof would have identified this even if he didn't know what the transporter was, and he didn't. Because you could measure lactate in the blood. You know, someone's exercising hard, with higher intensity comes higher lactate. So of course, lactate has to have a way of getting out of the working muscle into the blood. Now, what the Coris found is that lactate, one of the main recipients of that lactate is the liver. And then the liver will start to pull in that lactate. And then you could imagine that glycolysis pathway that I described earlier, where you take a glucose molecule and break it down and you get lactate at the bottom. What the Coris found is that when lactate comes into the liver, there's so much lactate coming in that it actually starts pushing that pathway in reverse. In other words, no longer is lactate a product of glycolysis. Now it's the origin or the substrate for gluconeogenesis, the synthesis of new glucose. That's the CORI cycle. But then, of course, we're not done. Once the liver has made glucose from scratch, from lactate, this gluconeogenesis, it can release the glucose. The glucose can come out of the glucose transporter on the surface of the liver cells, thereby giving the blood, dumping glucose back into the blood. Well, guess who can pull that glucose up and use it? The muscle. So the very tissue that gave birth to the lactate and those carbons breaking down glucose then receives those carbons back in the form of newly created glucose after having spent the glucose and turning it into lactate. That is the CORI cycle. So the CORI cycle is that the working muscle is relying heavily on non-oxidative glycolysis, thereby producing and releasing a great degree of lactate. The liver, being, as I've described it, the ultimate soccer mom of nutrient metabolism. It knows what to do with everything. It can pull in that lactate and turn it back into glucose through gluconeogenesis, and then release that glucose back into the bloodstream to then be taken up by any tissues that need the glucose for energy, including the muscles where the entire thing started. That's the CORI cycle. So it highlights this incredible efficiency in recycling these carbons or metabolites, converting what would be perceived as a byproduct, lactate, back into this heavily relied on and usable energy source, namely glucose.